Alright, so in this problem we are given three boxes connected by cords. One of these cords is wrapped over a pulley having a massless, a negligible mass, and the surface on which box A is placed is considered to have a negligible friction. We are given the values of the masses of the three boxes, and we want to find the tension in the cord connecting B and C when the assembly is released from rest. So we're looking for the tension here basically, and we are told that the system is released from rest. Now we can immediately deduce, once the system is released, that these two boxes, B and C, are going to accelerate downwards, while the direction of motion for box A is going to be to the right. And another important thing to note is that the acceleration for all of the boxes is actually going to be the same, the magnitude of the acceleration, and this is because we have one system moving together. Alright, now to find the tension between B and C, we might start by considering the box C and checking the forces acting on it. We would notice that we will have weight and tension, the tension that we're looking for. Now, if we apply Newton's second law on this system, we're going to see that we will have, if we take the direction of motion to be the positive direction, then the weight will be positive, the tension will be negative, and the acceleration is positive. We will get this equation. Now, this is what we want. We have the weight, we can calculate it from the mass. The mass here is given, but we don't have the acceleration. So studying box C alone will not be enough. If we try to look for other objects, the other boxes that we are given, maybe then we can get some more equations that we can use to eliminate the unknown that we have here. So let's consider box B plus C. So I'm going to consider two boxes at the same time, because this is actually going to eliminate the tension, which is an unknown for me. It will give me another tension, the tension that we have here. And this can be found, let's name this T1. It can be found by studying the tension here in box A. So we're going to study two more objects. First, we're going to study boxes B and C as one system, and then we will study box A. So if we do that, let's check what we will get by applying Newton's second law. So the sum of forces is equal to mb plus c times A. So here we have to consider both masses, and the sum of forces here will include the weight of B plus C together minus the tension T1, and this is equal to the sum of the masses times the acceleration of our system. So let's consider box A now. Sum of forces at A is equal to the mass of A times the acceleration. Like we said, the acceleration is the same everywhere. And for box A, if we look at box A, the forces that we have acting on A are this tension here, the weight, and we also have a normal force, unlike the other two boxes. So let's consider the direction first before we apply Newton's law. I'm going to take the horizontal direction because what I'm interested in finding is this tension T1 here, so which is a horizontal force. So I will apply this along X direction or along the horizontal direction. So we will have T1 only along the horizontal direction. We do not have any friction because we are told that the surface is frictionless. So now we got an equation with T1 and the acceleration here, and T1 and the acceleration here. So we can actually solve these two equations to get the acceleration and then substitute the value of the acceleration in Newton's law here for box C so that we can find the value of the tension between boxes B and C. So here let's solve for A. I will substitute the value of T1 here in the other equation. So we have WB plus C minus MA times the acceleration equals MB plus C times the acceleration. Let's take the acceleration as a common. We will have MB plus C plus MA equals WB plus C. So this will give us that the acceleration is equal to mb plus c times gravity over mb plus c plus ma, which is basically the total mass for all of the boxes. If we solve this, we're going to get 6.125 meters per second squared. So our next step is to substitute the value of A in the equation obtained for box C. So for box C, we got W minus T equals mc times the acceleration. So we will get that the tension is W minus mca, which is, this is W of C, of course. So this will give us mc into G minus A. And if we solve this, we're going to get a value of 36.7 newtons. This is the tension between the two cords, between the two boxes B and C. Now we still have part B. How far does A move in the first 0.25 seconds? So now we're considering box A. We want the distance covered for a duration of 0.25 seconds. So obviously we can see that we have a constant acceleration in this problem. So the type of motion is UARM. And then this means that we can write an equation for the distance covered. It's half AT squared plus V0T, if you remember the equations of uniformly accelerated motion. We found the acceleration, the duration is given. V0 is the initial speed. This is equal to 0 because we are told that the system is released from rest. So this gives us that the distance covered is just half AT squared. We found the acceleration in the previous problem, so we can just substitute its value, 6.125 meters per second squared, times the duration, which is 0.25, and this is also squared. If we calculate this, we will get 0.191 meters. So basically in this problem, we found a tension force by applying Newton's law, and we found the distance covered by one of the objects by applying the equations of kinematics for a uniformly accelerated motion.